Okay, let's get started. Last lecture, 15th lecture. I don't know, I mean, I hope it's useful for you guys. My lecture is useful for you guys. Let's see. So before we start, I think we will talk about the rule for final exam. Final exam. So the next week, the same time, here, the same time, and same location. Just next week. This is 065. The rule is the laptop, no. But the iPad or tablet is okay. But cannot use like how to say, like iPad pencil. How to say? Cannot use the pencil like a pen, like a e-pen. Yeah. So only the so only for as a reader. So it can be used as a reader. And before the exam, I will check the Wi-Fi needs to be switched off. Switched off. Whatever book is okay. You can book, notes are okay. That's the only yes allowed. Okay, those are cool. Those are cool. Is there any question about the diagram? Is there any question? I think I will send the role via e-learning. I think the last time I also sent e-learning. Yeah. Okay, so I will forward this one. Forward to differential geometry. Okay, I send the role to the widget. Also e-learning too. So, and then I have to mention that if you break this rule, so especially this part, the breaking this rule immediately, this rule. So immediately, these the fail. So be careful. Be careful. I don't want to give you F. So that's a rule. I already created the exam. Already created. The one is about like a vector field or differential form. Number one is vector field, and then differential form. Number two, homology, and cohomology. Cohomology. Number three, I don't remember. Connection curvature. Curvature. Number four, I don't remember. Riemann geometry. The content type. As far as I remember. Okay. Any question about the final exam? Okay. And then so I asked the TA to create the to grade the last homework as soon as possible. Yeah. You soon receive the graded homework, last homework, and then you get also solution. Any question? Any? So that's those are the contents of final exam. Okay, so let's get started. So last time, so we talked about connection and curvature. So that the connection is the connection. This one is just define the parallel transport, transport of parallel direction. Okay. So that you can relate position, relate the fibers, nearby fibers. so that this will be, you can differentiate. You can differentiate section. That's a okay. And in particular, power transfer, from power transfer, one can just see the Aharon-Bohm effect. Who should be last time. So in particular, so last time we just we wrote x at the section to the this way, and it has a bunch of properties. I'm not gonna write down everything. I'm not gonna write down everything. And then, in particular, if you use the local coordinate, and then you can write down like this way. So this mu is can be is a connection. Is in the element of one form of M and the Lie algebra body. Okay, Lie algebra body. So that's the local coordinate. One can just write down like this. And then curvature. Okay, so the curvature and the gauge transformation. So this local coordinate, you can only do that like as a locally. You can write down locally. So from one, so trivialization of vector from the U to the alpha or whatever. Then from this, the other trivialization of B, and from go to one to the other, so that mu is transformed like a G mu G inverse plus G D sorry dg G inverse. Okay, so that's the gauge transformation one will get from U to B. From U to B, so one will get the following transformation. And then the curvature is the curvature is the assignment of the two assignment so f x y and s, which is defined as roughly speaking, you can define like this. Okay, so that's the curvature one can define. And local coordinate, so this f, so the Persian mu, and the people written f mu can be written as the del mu and mu minus del mu and mu minus plus or minus, I don't remember. Like this. So I can define like this. Most likely plus. Okay, so that's the local expression for the curvature you will get. of course, in math, people write down one form. Sorry, this is not right way to write. So A mu is A mu dx mu is A. That is inside the wall. Okay, that's the inside. The same thing. So this. Okay, so this is two form. And the Lie algebra body. And the gauge transformation is and then F can be written dA plus A which A. Okay, and then F mu is transpose gauge transformation GFG by gauge transformation. Okay, so that's what we saw last time. Okay, and of course, if the special case is when G is U1, and U1, this term is gone, this term is gone, and then this term is gone. Okay, and then this corresponds to Maxwell. Functional theory. So everything commutative. So abelian engagement. Gauge theory. On the other hand, so that the gauge transformation is just reduces to. So if you write that G is equal to E to the I lambda, okay, then what you get is the A mu is up to Z or lambda, down lambda, and lambda is purely imaginary, like this here. Sorry. So this is a gauge transformation. So everything commutative. So G A, G inverse, everything commutative. So G can be bring to left, and then they will get 1. So those are gauge transformation for Maxwell theory. On the other hand, so for generic Lie algebra, so this is a transformation of the curvature, so that S Young Mills people just write down like this way in order for the action to be gauge invariant. So I mean, so it's the reason why we need to put the trace is that trace F which star F is mapped to trace of G inverse FG. G FG inverse. Okay. And then G inverse and G cancel, and also it's trace, so this one can bring to here. So you cancel, and this is equal to trace of F wedge star F. Okay, so that's so therefore this quantity can be defined as entire manifold M, entire manifold M. So they cancel. So the quantities can be defined entire manifold or entire manifold M. Okay. So therefore this action is well defined. Okay. And then yeah, we saw that last time the equation motion and so on. Okay. equation motion is something like a star dA f star is equal to 0, and the dA f is equal to 0. So the two. So this is equation of motion, and this is the Bianchi identity. Okay. And then dA is of course d plus a, like this. Okay. So this is called Yame's equation. Any question at this moment? So, and then the interesting thing is that this one is bounded below. So this action is bounded below by the point 1/2 g squared unknown. Trace is greater than equal to FHF in 4 dimensions. When so dimension is equal to 4, so this is the case. So here there is no star. Okay. So this is there is no star. So to show that you need to do the following trick. Yeah. So let's consider f is equal to f plus f minus, where the f plus satisfies the following equation, and f minus is satisfied the following equation. Okay. Oops. Sorry. So if you decompose like this way, so one can show that the so if you decompose like this way, one can show that so this one is equal to the inner product of f plus, and then f minus. Okay. On the other hand, this one can be shown that the f plus minus f minus and f minus. Okay, so one can show like this one. Yeah, of course, the this quantity f plus and f plus is just some number times trace of f plus, which star f plus, like this one. And then likewise f minus is like this. Okay. So one can show like this way, and then each term is the positive definite, so one can bound it. So like this in 4 dimensions. So therefore, if f minus is equal to 0, equality holds. So this equality only holds f minus is equal to 0. Equality holds if only if f minus is equal to 0. F minus is equal to 0. Okay, that's the case. F minus is equal to 0. And this equation is called anti-self-tail equation. Anti-self-tail. So f minus is equal to 0 is that the f satisfied. Okay. So this means that the this means that the f satisfied like this one. And this is the self-tail equation. Or instant. That is called instant. And then these instantons play a very important role in modern mathematics. Nowadays it's called gauge theory. So everything starts with the Atiyah Hitching Drink of Money, 1707, and so on. Atiyah, and also Donaldson's ball, and also Atiyah Bott, and so on. Anyway, the difficulty of Yang-Mills theory is that the so because of this term, so these Yang-Mills equations non-linear. Non-linear equation. Okay. So therefore, the solution space is no longer linear space. Solution space is somehow curved, and with lots of singularity. And you have to deal with this kind of like singular behavior. And yes, those are, you have to do a lot of analysis in PDE or like so on. Those are hard part of this case here. I have to spend lots of time to deal with this nonlinearity. Any question at this moment? Okay, a little bit about the history in the physics side. So to motivate you guys to how to study the Yang-Mills, so this is 1954 Yang-Mills. And then it's very well known that the like many people around that time knew that how to construct this action, how to construct many people around that time. Many people. One of them is Howard. And Yang gave a seminar at IIS, and then Pauli just asked like a merciless question: is the what is the mass of this the bosons that carry? What is the mass of this Yang-Mills bosons? Okay, that's spin 1 here. As you can easily see, so in physics you need to count the so-called mass dimension. So mass dimension of this one is 1. And sorry, maybe I should mention that so the mass dimension of A is equal to 1. And F mass dimension is of course the 2 because it's dA plus A which A. And D has mass dimension 1, A is mass dimension 1, so therefore this is 2. And then of course the same thing happens with star F, for in 4 dimension this is also same. So this has a mass dimension 4. Okay? And then so in 4 dimension it's become massless. So this means that the GML is the coupling constant is dimensionless. So therefore, classically, there is no dimensional two parameter. There is no dimensional two parameter. So classically it should be massless. Okay. Classically it should be massless. So both Pauli and Yang knew classically it should be massless. But if the people believe that if it is a classical massless, we should be able to observe this particle at around that time, mid-90, like 50. But of course, there is no such a particle is observed. I mean, of course, like the bosons should, so the mu should corresponding to spin one, massless boson with non-abelian. Okay, non-abelian gauge boson. Gauge boson. Okay. If it is abelian, so we can see the, I mean, you can see the blackboard because so here the light is emitting photon and it just hit the blackboard and it just go to your eye. That's what you can see. But there is no such particle is observed in low energy scale. So that's the Pauli's concern. There is no such a, so is this really, does this action really describe a nature or not? That's the question of Pauli. Because Pauli also knew one can construct such an action, but it doesn't, Pauli believe doesn't describe nature. So, but after that, like using this this Yamia theory, people start creating the many things. So mid 60s, Higgs mechanism, Higgs cross-poles, and also Weinberg so and Salam constructed using the electroweak theory. Based on this, based on the Yamia theory. So the still class, like the proposal is still classical. I mean, yeah, the quantum nature of Yamia is not understood. And the quantum nature of Yamia is literally the 70s by the super genius by Edward so that what they mention is that so if you include this quantum correction, so what we need to do is you need to consider the path integral and so on. If you include so the non-perturbing factor is important. Proof to mention the non-perturbing effect is important. And then the strangely thing is that this coupling constant in quantum mechanically, coupling constant will change the energy. So this is the energy scale, and that's the G Yamna's coupling constant. And this energy, if you go to F, like high energy, it behaves like a really like a classical. So if you go to high energy, it becomes the really like a small body. But if you go to low energy, it becomes really very strong. Very strong. So this is called asymptotic freedom. It's called asymptotic freedom. So GMS is small means the theory behaves like free theory, like anyway. So it behaves like a really classical. But if you go to the low energy, somehow coupling constant become big, and the non-quantum effect become important. That's the in 70s proved, and some other people like a Gross, Wilczek, Politzer, and so on. So that's the and then if you go to the sum scale, this is called QCD scale, lambda QCD, which is around the 300 MeV, 300 MeV, and then the really coupling constant goes to really 2 squares, and then non-quantum effect becomes very important. And then moreover, so therefore, if you go to the QCD scale, the gluon. So this mass is no abelian gauge bottom, which is called gluon. So gluon. Just gluon has a, as I mentioned, it has a color. So the gauge group QCD is G is equal to SU3. Okay, and then it has a color. So 3 colors. So red, blue, green, cyan, and salt. So gluon just form the glue ball. They become color singlet. They become singlet. They become white, and they acquire mass. Acquire mass. So the classically it should be massless, but quantum mechanically, if you go to low energy, it becomes massive. The particle will have a mass. Okay. So that is for mass gap. So this is for mass gap problem. Mass gap. This is for mass gap. And this mass gap is for one of the millennium problem. So to understand the mass gap, you literally need to understand that that's the non-quantum effect, or like a, which is really, you need to taking care of this pattern, infinite, but which is not mathematically well defined. Okay, so the connection divided by gauge transformation. So that is the difficulty of study of QCD. But this story is roughly understood in like a mid-70s by thanks to Oracle. Maybe I should Oracle. Okay. So therefore, even quantum mechanically, this Yang-Mills theory is very difficult to study, and mathematically, it's also very difficult to study. Yeah, 1982. Use this the instant modulus space to construct so-called four manifold invariants. And so the analysis is very difficult thanks to the due to this non-linearity. And in physics side, even like because of non-quantum effect, so there's a so-called the theory of mass gap, and also it's confined. So it becomes color singular and confined. For confined. So in the low energy, it's hard to take only one gluon out of the gluon. It requires infinite many energy. So always try to become color singlet, but you cannot extract one gluon out of that gluon. That's why you cannot observe in low energy. In the gluon, you cannot, but you cannot take one gluon out of the gluon. And the gluon is way massive than the ordinary low energy scan. That's why you cannot observe gluon in the nature. So, but if you use so large hadron collider and so on, if you use like a high energy, you can just extract some image. That's really. So 1954, Young Mills just proposed this action without understanding any physics, but the mid-70s, finally people start understanding what's going on. So it took like almost 20 years to really what's happening in this quantum memory. But okay, any question at this moment? So that's the introduction of the mass gap. Because I mean, people just mentioned it. What's the meaning of mass gap? And the people do not explain. Even like if you take the gauge field theory, or like a KFT2, people usually do not explain mass gap problem. It's a good place to learn. Okay, so those are review from the last week. The only review, just give you some bit more information about them. Bit more information about gates here. Okay, so fine. Okay, so let's any question? If not, I'm going to talk about so-called characteristic classes. 序型类 character classes. Like there's another translation to general layer, but that is not the commonly used translation as far as I understand. Fine. So those are what we're going to learn. So in the homework, you already saw the following thing. The homework, you just consider the how to say your bundle, or like your bundle over a sphere. For P and then S2 and the U1 bundle. So go bundle. And then just put some connection on here, and then what we saw is that the 1 over 2 pi S2 F is really quantized. Is N. Yeah, actually, so in your example, yeah, it becomes 1, actually, as far as in the So that is what Dirac constructed. So Dirac monopole. In the homework, you constructed like a gauge configuration that will give you this when n equals 1. So that Dirac monopole is, as far as I remember, around 1930s, as far as I remember. Before the theory of like how to say connection of fiber bundle, or characteristic is constructed. And then so this is the, I don't remember, around 1930, I don't remember. And then 1940, of course, Chen and Chang, and also from Dragon, and also Stiefel, constructed topology character classes based on the theory of the vector bundle or principal bundle. So that's briefly we would say. And in fact, so this guy is treated as the first channel. The first channel class of vector bundle or principal G bundle, whichever is okay. So this is the first channel class. So that's we will study. So the Dirac example is the one of the simplest example of the characteristic classes. A Chang and a Pontryagin and a Stiefel with me largely give a larger generalization of Dirac. Okay. So what we want is that the idea is this use curvature or connection obtained using. Idea is the obtained the cohomology, obtain the cohomology class. HK and Z, some inside cohomology class. So you start with vector bundle or principal G bundle, which way is okay? Principal G bundle. So you can start, if you start with the principal G bundle, one can always construct the vector bundle using associate bundle. So and then the connection here can translate in the connection here. And using that one, using a connection and curvature on this principal or vector bundle, one can construct the cohomology class in the base manifold. Base manifold means that the base manifold. And the important thing is here. Important is integer coefficient. It's an integer coefficient. So this is integer coefficient. So that if you integrate base manifold, you get that integer here. It's not R. So not only R, it's just Z. That's important. So that's the main idea of the Okay. So to get the base manifold, the cohomological base manifold, you really need to recall the gauge transformation. It has to be invariant on the gauge transformation to be well defined. To be well defined. So therefore, so you need to do the two construction. So one is that the so this is just a trace of. Okay. So if you put the G inverse and so on, so if it is inside a trace, of course it's invariant on the transformation. Also, if it is inside a determinant, it's invariant under this gauge transformation. So therefore, it's globally well defined. Okay. In fact, so they are related. So the two constructions, they are related. So sigma 1 is S1 is equal to, sigma 1 is equal to S1, sigma 2 is equal to 2 times sigma 1 is equal to S1 squared minus S2, 3 times sigma 3 is equal to sigma 2 S1 minus sigma 1 S2 plus S3, and so on. So it's just different way of describing. And then of course sigma k is, so since f is twofold, so sigma k is 2k also sk. To show it's a cohomology class, we need to show that it's closed under the D. So we need to show, number one, need to show. So D Sk of F is equal to 0. It's a closed form, namely B 形式 closed form. Number 2. So we know that the given vector bundle, the way you put the connection is not unique. Okay? So even the Riemann geometry, given a tangent bundle, one can construct lots of connection, but the uniqueness only comes from metric compatibility. Remember? So there are lots of ways to construct the connection, but the ones which satisfy is the compatibility of connection. So this is metric compatibility. Then you will get the unique connection, so-called Levi-Civita connection in Riemann geometry. But unless you put this condition, metric compatibility, there are lots of ways to introduce connection. So the question is it independent? So another thing is independent of choice of connection. Okay, on the vector bundle. So we need to show two things to show that it's really the cohomology on the base manifold. Okay, so let's first show that this one. So D trace of Fk is the trace of df dot Fk minus 1. Okay. Okay, and we know the df. Sorry. So we know the df is equal to 0. So beyond guarantee, which means df plus a wedge f. So this means that the df a wedge f plus f wedge a. Okay. So this means that the df like this. Okay. We need to show and plug that into here. So. Okay, but it's true that this f can be inside the trace can be put. Oh, sorry. This should be minus. Sorry, it's a bracket means this is minus. So therefore this is plus. This is. Okay. So this f can be just put to the put inside the trace. F can be just bring it to here. So this means that this is equal to 0. Okay. This is AFK. So this is minus trace of AFK and plus the trace of AFK. Okay. So this means equal to 0. Okay. That's what you obtain. So, and since the sigma can be written in terms of S, everything S, so therefore d sigma k is also 0. So therefore it's a crossroad. Okay. It's a crossroad. Okay. So number 2. Okay, number 2. Number 2, you need to show that it's invariant under the connection. So this is number 1. Number 2, suppose A is transformed like A plus A. So there is some small deformation of connection. Okay. So then, delta trace of Fk is the trace of delta F of Fk minus 1. And then, so the K of them. You have a K of them. Okay. And then, so this delta F is indeed trace of like this way. Okay, like this way. And then now you apply again this identity. You apply this identity, and then this is equal to k times trace of d eta fk minus 1, and plus minus minus eta df dot fk minus 2. Okay. So let's do one by one. So, sorry, a which f is equal to, from here, fa minus df. So that's the case. And you apply af here in the right hand side, and then this one will give you plus eta f df sorry fa and fk minus 2. Okay, and this one is the last, and plus eta fk minus 1. Okay. So that's the case. No, so since this is one form, it should be minus. It should be minus. So here, a eta fk minus 1, and if you bring a into the right, since a is one form, you get the extra negative. And again, you just apply af is equal to fa minus df here. Then so this one is equal to k trace d eta fk minus 1 minus eta df fk minus 1 minus 2, and here again eta f df fk minus 1 k minus 2, and so on. So then what you get is the plus f square, eta square f square a fk minus 3 minus eta fk minus 1. Okay, so that's the case. And do the same thing. So now, so here we just push this a to the right. So here now is the previously f a f k minus 2. Now f square a f k minus 3, and you push a to the right. Okay. So then this degree, the exponent will increase. This exponent will decrease. And instead, at the cost, you get this df in the middle. And if you push a to the right, the final a here, this will cancel with this guy. Okay? So therefore, what you get is essentially k times trace of d eta f square df f k minus 3 and dot and add f k k minus 2 df. That's what you get. But this is nothing but so this is nothing but this is equal to k times trace of d8 fk minus 1 minus k minus 1 8 df fk minus 2. Okay, that's what you get. So essentially, if you have a k minus 1 copy of, so again, this f can be just moved to the right, f squared can move to the right, and what you get is k minus 8. There's something strange, k minus 1. E? Sorry, I'm doing something stupid. This is k minus 3. This is k minus 4. Yeah. This should be 3. This should be 4. This should be 3. So that's the case. And in fact, this is equal to k times d times trace of eta fk minus 1. Okay? So d acts on eta, you get this one. D acts on f k to the k minus 1, you get this one. Okay? So now for this variation of the connection. So variation of connection just leads to just exact form. So D of something. So therefore it doesn't affect the cohomology class. So it doesn't affect the cohomology. Therefore this is the exact form. So doesn't affect the cohomology. So therefore, so it's independent of the connection. And also it's a closed form. That's how you construct. That's how you construct a cohomology class in this manner. So let's start with the consider the real vector bundle. Vector bundle. from E to M. And then so since independent choice of connection, so it only depends on vector bundle. So this means that the independent of the choice of connection means that this quantity depends only on the vector bundle. Okay. Okay, so. So vector bundle, so and then you can just impose the metric on each fiber, EP, each fiber EP. So therefore, then you can take the orthonormal frame. So this means that you can just consider the oriented. This means that structure group G can be just considered SOR. Okay. SOR. So therefore, the connection F is a twofold in the reachable value SOH, SOR. Okay. The connection. And then okay, so the SOR satisfies the following condition: F plus F trace is equal to 0. So the Lie algebra SOR is this satisfies the following condition. So this is an anti-symmetric matrix. R by R matrix. Okay. Therefore, trace of F if K is equal to K is odd. K is odd. Can you see this? For instance, when K is equal to 1, is equal to 0, and of course this is equal to 2 times trace of F, which trace is F is equal to 0. Because it's anti-symmetric. Likewise, when K is equal to R, always this is equal to 0. And as you can easily see, unfortunately I erased it. So therefore, one can only define the contract number like this way. So this is 4 and so on. And then contract number P of K of E is a contracting class is the defined as the this is 2 pi squared, and this is 2 pi to the 4th, defined as a 1 over 2 pi 2k sigma 2k over E. Okay. So that's the differential contract. So this is the called the contracting system. So this is the indeed H4k of N and Z. So 2k. Sorry, this is 4k. Okay. Okay, so let me give you an example. Hey. So let me give you an example. Let's see. So P1 of E is the order 4 pi square sigma to F, which is the 1 over H pi square. And then we already know trace of F is equal to 0. This is 0. Therefore, this means that this is equal to minus 1 over H pi trace of F wedge F. F squared is F wedge F. Okay, so this is exactly what we saw in the before in the YAMLs. So the trace of F which star F is bounded by trace of F which F and so on. Okay, so that is a first point tracking class. So this is called first point tracking. Every case point tracking. And then yes. And I saw that the Chinese translation from tracking is super complicated. It's super complicated. Hunter, anyway. So that's case. So therefore, so it's always multiple 4. It has a multiple 4. So that's coming from real bundle. Yeah. In particular, so in particular, the F can be written as the point. So the 0, x1 minus ix1, 0. So you can always, how to say, the block off diagonalized by gauge transformation and so on. And 0, 0, ix. Like this. Like this. And then xk is the real So in this case, trace of F wedge F is more like a sum of xk squared some number. K is equal to 1 to the F. So of course F is something like R over 2. Okay, so that's a 2. Something times 2. Okay. That's an example of the character class. Okay. How about complex case? So this is real R vector bundle. A complex case is studied by Cheng. Okay, so the complex rank R vector bundle. So E to M. So again, the same thing. You can just impose the Hermitian metric. So the complex case impose Hermitian on EP. So then, the structure group is a unitary group, 有群, and this means that the F is inside 2 from M and R. So this will satisfy. So they satisfy F plus F dagger is equal to 0. Okay. F plus F dagger is equal to 0. Okay. So this means that the diagonal entry. So you can diagonalize. So this is F is log of diagonalize. F is something like this one. Ix1, Ix2, diagonalize X, say R. You can diagonalize. Okay. And then diagonal entry is always the purely imaginary. Because I mean X plus X dagger, so it has to be purely imaginary. Okay, that's the case. And then Chern class is therefore, so the Chern class of E is determinant of 1 plus I times F to pi. Okay. And this is 1 plus C1E plus C2E plus CRE, where CK of E is equal to I over 2 pi of K sigma K F. And this is inside. Like this. Okay, that's good. So therefore, C1 of E is just I over 2 pi of sigma 1 F, okay, which is the I over 2 pi trace of F. Okay, so this is exactly what you saw in the Dirac model. So if G is U bundle, R is equal to 1, this is the Dirac monopole configuration. Dirac's monopole. So essentially what we saw is trace of F. Okay. So if you integrate over S2, you get the integer. Okay. And then it's a huge generalization. minus 1 over 2 pi sum over xi. I is round for 1 to r. And this x, so if you can diagonalize always by gauge transformation like this way. So this xi is called it's called Chern root. How to say Chern root? It's called Chern root. These xi are called Chern roots. C2, I just give you expression of E. Like this. C2E is given 1. Okay. And so on. And a little bit explain how the connection to the Dirac monopole. A bit more about the Dirac monopole. So here, so Dirac monopole is the R is equal to 1, which means the line bundle. You just consider line bundle over S2, okay, and then you just consider C1L. You just consider C1L, and then integral over S2, and this is equal to I over 2 pi, and then S2 of F. Okay, and this is integer. Is some number is the integer number. So that's what we saw in the exercise. And then, as I mentioned, this is only depends on the vector bundle. Okay. So vector bundle is essentially, as I mentioned, so the construction of the U1 vector bundle. So here, so if you have S2, sorry, I just keep talking about. I forgot to take a rest. So the S2. So this is S2. Okay. And at each point you have a fiber. Fiber is line bundle. Line bundle means that in complex case it's just C. C. And you can always cut out the unit circle here. Okay. Unit circle. Then you get the S1 bundle. Okay. So S1 bundle. And as I mentioned, S1 bundle, S2 is just how to construct. Is just how to construct is you have the northern hemisphere and southern hemisphere, and you can consider S1, and then the question is the how do you group along this equator? So that's the case. And then you have in the equator you have a torus, and then the equator you have another torus. When you glue them together, okay, you glue them together, you can just do the n-term rotation in the meridian. Okay. So this n-term rotation is really coming from this end here. So monopole is just how vector bundle is twisted around the equal. Okay. Almost done, but let's take a break for 10 or 15 minutes. And then I will wrap it up later. Let's take a break. Short break. Okay, if you don't need to take a break, I can continue. Okay. Okay, go ahead. If you want to take a break, let's take a short break and then. Okay, let's get review. So we are almost there. Okay. So therefore, so this curvature here is just define the magnetic flux. And then also for this temperature glass appear in the so-called quantum integer Hall effect. It's just anyway. So I'm not going to explain. I'm not going to what is the integer Hall effect, but Another appearance in physics of the first Chern class is the integer whole. Okay. So another way of defining the thing is that the so a Chern character Chern character. So this is a different basis. Chern character is something like this. Like this, right? Okay. So for instance, Chern of 0 e. So what would you get? So let's see whether you are awake or not. What would you get? Chern 0 b. Almost there. F is R matrices. R matrices. So here, so trace of R matrices. So therefore it should be R. Chern 1 of E is the same as the first Chern class of E. Character of 2, second Chern character is something like 1/2 E1 squared. Like this one. Yes. So the reason why Chern character is important is that it should satisfy the following case. You have a direct sum or within sum is behaved like this way. And also you have a tensor product is satisfied the following way. So on the other hand, okay. On the other hand, yeah. So on the other hand, this determinant construction. So here is just trace construction. Trace construction for Chern character, but the Chern class just is determinant construction. Okay. And then use determinant construction So C of E1 plus E2, determinant construction C of E1 with C of E2 is not true. Okay, it's not true. So here trace construction, this is determinant construction of characteristics. But if you use this one, this no longer holds. That's the difference. That's why Chern characters behave very well in the construction of the vector bundle. So that's the even though it's a different basis. Okay, so that's one property of the another property is that so we construct a Pontryagin class. Pontryagin class. So what's the use of Pontryagin class? So one thing one can use is the so-called Hirschberg signature theorem. So that's the closed oriented, the closed oriented or manifold. Then you can just define the of M4 to H2 of M4. So Hodge star will give you map H2 to H2. Two form to two form. And we already knew that the star square is equal to what? Star square is equal to 1. And so therefore, if you diagonalize, so this is just a linear map. Okay. So if you diagonalize this linear map, so what you have is the eigenvalue should be either +1 or -1. This is Hodge star. Because I mean, Hodge star square is equal to 1. Has to be 1. Therefore, either +1 or -1. And then, so the number of the dimension. So number of plus, let's call this one is n plus, and then this is n minus. So then signature of n4 is called n plus minus n minus. And this is a topological invariant. And then what Hirschberg mentioned is that this is indeed equal to 1/3 Pontryagin number. First Pontryagin number n4. So regardless, the first Pontryagin class is a 4-fold. So therefore, one can integrate of a 4 manifold and you get the integer. You get the integer number. And then that is equal to, in fact, the signature of the M4. So this is the Hirschberg signature theorem. And then this is also another way. So P1 M4 can. This is another way to think the connection between topology and then the differential manifold. So that the right-hand side can be obtained by just using differential forms and vector bundle. The right-hand side is just topological number. It's 3D M4 topology now. So it's a very like a similar flavor of the Gauss formula here. And in particular, this is can be obtained by locally. Just each patches, you get some 4 form, and if you integrate out of M4, you get the topological number. Okay. So this is also another instance of connect differential geometry and topology, and from local to global. And this signature plays very important role in many things, like a K theory or index theorem, and also it plays a role in the constructing Milnor's exotic field. Anyway, I'm not going to explain what it is. Okay. And also, so this P1 force of M4, or this is M4, is usually related to instanton number. And another question one can ask is the contracting class is a real vector bundle, and Chern class is a complex vector bundle. What's the relation between them? Is there a relation? Yes, there is a relation. Suppose we just complexify. So so this is a real vector bundle. So this is a real vector bundle, and this is a complex vector bundle. So if you start with a real vector bundle, you can complexify by EC E cross C. Okay. And then so that the pk of E is given by -1 to the of C to K and E C complexified. Okay. So that's the case. And in fact, if the C, so therefore in the complex vector bundle, so if C2K, if it is K, okay, say I E C, okay, odd is equal to 0. Is equal to 0. One can show that. Only even Chern class will survive non-trivially, but the odd Chern class is equal to 0. This can be easily shown that the this can be easily shown that if you EC as a vector bundle is the isomorphic to EC complex conjugate. So therefore, one can show that the so from here one can show that the CK C odd CK EC is equal to CK EC. But on the other hand, from the Chern class construction, one can show that this is equal to minus K CK E bar of C. So when K is odd, it has to be. That's a relation between contracting class and Chern class. Okay, and okay, so that's the construction. So another class is called this is a relation between contraction and chain class. Another class is Euler class. Again, is a vector bundle. Is a real vector bundle. So in this case, as I mentioned, F will take the following form. Sorry, so 2R vector bundle. So this is a 2R rank. And then, as I mentioned, so F plus F. F trace is equal to 0. So therefore, F can be written as the following: x1 minus x1, 0, 0, x2 minus x2, 0, 0. Yeah, and so on, as I mentioned. So the last time I put the I here, but I don't need to put the I, sorry. So this is okay. And then XR, 0, XR minus 0. Yes. So you can just blockwise and then downwise. Okay. And then, if this is the case, one can just take so-called Parthian of the matrix. So the essential Parthian of F, we just pick this component. So that is the product of x1 to total xr. Okay. So therefore, Parthian of F squared is equal to determinant. Determinant of F. Determinant of F. So you just pick, I mean, proper definition of the Parthian is something like this, and proper definition of Parthian is something like if you start with like this way, 1/2R R dot sum of a sigma in the symmetric group of 2R F sigma 1, sigma 2, F sigma 2R minus 1, like this one. Like this. Okay. And in fact, so this way one can show that the Parthian of G F G inverse is equal to Parthian of F. This is invariant gauge transformation. So you start with even dimensional real manifold. So one can, and then E Euler class of E is Parthian. Okay. So you get top form. you get the topo. So M is okay. 2R. So therefore, if M is the even dimensional manifold, and in particular, you just consider the tangent bundle of M. Okay? You just consider tangent bundle of M. So then this can be integrated out in the manifold itself, because M is a 2R dimensional manifold, and then tangent bundle is 2R rank 2R vector bundle, and from Euler class you get the top cohomology, top degree cohomology. So integrate out, and this is a deep theorem by Cheng. Cheng. This is the Euler characteristic of it. That's why it's called Euler class. And this is called the Gauss Bonnet chain theorem. Okay. So to get the Euler characteristic, you have to take something called some procedure called Pfaffian. So this is a higher dimensional generalization of the Gauss Bonnet theorem by Cheng. Okay. Okay. So dimension. So this is the Euler class, and then for Chang class, as I mentioned, so F can be just write down I x1, I x2, I xr. Maybe you can just So then this, in fact, the term of E is a product of 1 minus xk divided by 2 pi, and the k is equal to 1 to r. One can just write down like this way. So this x1 and the xr are Chang root, and then everything inside xk is h2 of n. Okay. And then you can just take a product. So suppose you have a line bundle whose Chang root, this xi or xk or the Chang root is xk. So therefore, this is called splitting principle. So suppose you have the Chang root is something like minus xk divided by 2 pi. Okay? So then Chang of E is equal to Chang of L1. Chang of L1 plus L2 plus LR. Okay. Okay, so this means that this one is indeed equal to Chang of L1, Chang of L2, Chang of LR. Okay. Like this, we can just write. Because here E is a vector bundle, so this is a vector bundle like R, vector bundle, and K is a line bundle, but you cannot distinguish between these two bundles because by Chern class, because if you diagonalize it, Chern root is just can be a personal line bundle, and then of course E is not isomorphic as a vector bundle. L1 plus L off. It's not isomorphic to vector bundle. However, for Chern class, they cannot distinguish if the Chern root is the same. So therefore, so this means that this Chern class is not a strong topological invariant. It's not strong topological invariant. You cannot distinguish the genuine vector bundle and the tensor product of the line bundle. Chern class. This is called Grothendieck splitting principle.分裂原理。分裂原理。Okay, so those are the so those are the property of the character Chern class of the. Yeah, 30 minutes has left. I don't think it's eliminating to go to talk a top class or disregard class or error genus. I don't think it's okay. Let me give you some flavor of the okay, so those are basic property of a characteristic classes that appear as a generalization of the Dirac model. Okay, I think we'll just give you the basic property, telling basic property of the character classes today as a generalization model or Gauss-Bonnet theorem too. Okay, let me end by just briefly mentioning the index theorem and so on. So if you learn the quantum filtering, the first thing you learn is a free boson and free fermion. And for free fermion, you just have the following action. And then Dirac operator, and or maybe not or this way. Or maybe these or like this way. So you just have you can have, so this is called Dirac operator. So Dirac operator, so it can be written as essentially the so-called gamma matrix in the covariant derivative like this is given. And if this gamma matrix is satisfied, so for group of algebra, 2 times 2 in the in a Riemannian geometry. And one can define, one can define so-called index of this group Dirac operator as a kernel. So this Dirac operator is called just map spinor to the positive spinor to the negative spinor. So and then the section of this spinor bundle is this the Dirac kernel. Dirac kernel has the so-called focal point, and then positive spinor and the negative Wald spinor, and so negative Wald spinor. And the gamma matrix is the 0, 0, some power matrix and so on involved. I'm not going to be, so therefore the plus is mapped to minus, minus is mapped to plus, and so on. So that's the map you get. And then if you just consider kernel of this map minus co-kernel of this map, Dirac operator. And then at the end, single bot will tell us about this one is equal to a roof genus of tangent of So CH is a channel character, and a roof is called a roof genus, which is some kind of character classes. Maybe I can just show that the by using character the channel root over there, so one can just write down the a roof of bundle E is in this sinch E to the xk, and product of k is equal to 1 to r over 2 minus E to the minus over 2 xk, like this. So this is called a roof genus. So xk is the channel root of the vector number. Okay, so left-hand side is some kind of analysis. You just use analysis to define the left-hand side, and the right-hand side is some kind of like can be defined a topological let's say the character has classes, and this is called a single index. Index. And also the Gauss-Bonnet theorem or Kitzbühel-Kramer lock and so on can be also defined as the characteristic classes. Even Kitzbühel signature theorem is also defined by formulated by the part of it, like a big index theorem. And then always in this and then yeah. So the Gauss-Bonnet theorem is the d plus delta is equal to order class of tangent bundle, like this one. This Gauss-Bonnet theorem is so left-hand side is always something like some analytic index, and right-hand side is some kind of topological index. So this is a Gauss-Bonnet Chern class. We can just define also Kitzbühel-Kramer log. One can define the so-called Doppel complex and so on. And then one can define, we can show that the Kitzbühel-Kramer log. So in this case, Kitzbühel-Kramer log and Doppel operator. And it's a complex order, Chern of E plus now top class of M, tangent bundle. Homomorphic tangent bundle. So So the top class is also very similarly defined. E is k is equal to 1 to r x k, 1 minus e to xk, like this. It's very simple. This is called Hughes-Green law, and this is called Gauss-Bonnet-Chung, and then this is a finger. And so those like a big theorem can be just defined. Left-hand side is some kind of like an elliptic operator. So elliptic operator, which is some kind of differential operator with certain properties. And right-hand side is just integrate over the manifold on the integral of the character classes over the manifold. So that's the flavor of the index theorem. And like this. So that's the character classes play a very important role in the single index theorem. And then that again has a physics application, but I'm not going to go into the detail. Anomalies, supersymmetric quantum field theory, and so on. But that's not in. Okay. Any questions today? If not, let's stop here, and then thanks for the attending the lectures. I hope you enjoyed. Okay, let's stop. Yeah, anyway, see you next week. Yeah. Let's stop here. What's the question?
I'm not sure whether it's still worth
Going there?
as a project.
So the periods when to when?
From the middle of September to
December.
10 weeks.
10 weeks?
Yes, 10 weeks.
10 weeks is 2.5 months.
Yes.
So you will be back around the end of November or like December?
Yeah.
The beginning of December,
Yeah.
something like that.
Yeah. So since there isn't feature the cure theoretical or
Okay.
I'm not sure whether it's still
Santa Cruz.
yeah, Santa Cruz. I don't know.
Santa Cruz and San Diego is close? Is it close?
I know that it's around 100 kilometers away from Berkeley.
Berkeley?
Yes.
Oh.
Just about 100 kilometers.
Santa Cruz. Let me check the position. Santa Cruz. I forgot the words. Do you have a question?
No, I just want to thank you for the lectures.
No problem.
Yeah.
It's my job.
I'm a math
Yeah. Okay, you just audit?
Yeah,
No,
I
no
take this
credit.
course for free. So.
I see.
Yeah.
So you're not gonna.
Yeah, and your lecture notes and something you wrote on the website.
Okay, thank you. Bye-bye. Oh, yeah. Courses. Oh, I see. Okay, I don't know. It's up to you. But you're going to apply, right? Are you going to apply US?
Actually, I'm not thinking strictly since, first of all, my family could not afford for some
Many application?
probably since my family is not as rich as United or so on, and further, there are too many obstructions during the way of thinking about me, such as I didn't get the like TOEFL. I get TOEFL yet, but the recommendation from US, for example, I couldn't get recommendation letters from Santa Cruz. Yes, and currently I'm thinking about just have my PhD essay. It's really great.
I see.
And for example, my COLA is really great. And
Okay.
also this course is about research this semester, and this research fields about VOA is like to my taste.
Okay.
So I'm just thinking about
What is famous?
Yes. If I'm thinking about the things, maybe the opportunity to you see is not that necessary in some sense.
I mean, Santa Cruz.
Yeah. Even
So when is the application of this famous? This summer?
this summer. I'll go to their campus, take some tests, and that's good.
I don't know. It's up to you. It's up to you.
Okay.
Yeah, it's up to you.
And the only benefits, in my point of view, to go to Santa Cruz is to just see the world around.
Yeah, that's true.
Yes.
I mean, yeah. I mean, 2.5. It's up to you. I mean, it just suits. Yeah, California. Yeah.
Yes.
Enjoy that. But that place looks very peaceful.
Yes.
The Santa Cruz looks peaceful.
Yes. It's built on the mountain, and
Yeah.
the sightseeing is great.
Yes, I think. So if you want to do this kind of stuff for 2.5, yeah, it's okay to go there. I don't know. It's up to you.
Okay.
But if you want to focus on serious study,
Yes.
you can stay in China. Yeah. Yeah. Okay. So you're going to Siemens.
Yes.
Okay. Sounds good. For Santa Cruz, you should make your mind. I cannot say anything.
Okay.
If you want to enjoy your life in US for 2.5 months, you can go. Otherwise, you can stay in China. It's up to you.
Okay.
Yeah.
I'll listen about it.
Yeah. So, what happened, Zaichi? Did he?
You mean Sophie?
Yeah.
He might take his master in US.
In Sound Center? Oh, Sound Center.
I forgot.
Stony Brook, right?
Yes.
Okay, he didn't get an offer from Northeastern. No, Northwestern, but Northeastern.
Yeah.
He mentioned he's listed as shortlist. He's in shortlist of Northeastern, but
the last time talked to me that maybe I will first check the name.
yeah, it's now really crazy. US, I mean, it's really less chance. Application in our field is really less chance. And then even Zanichi, he already received like, and he applied like 20 schools, something like that, as far as I remember.
Last time the entity said just apply for the PhD in Singapore, and if you fail to the PhD in Singapore, you'll receive a master offer. And the last time he said that he planned to just receive his offer, and after he finished his master, he will try to apply for PhD in the US.
Yeah, anyway.
Okay.
Okay, staying serious is also good. So, okay. Yeah, and then okay. Next year you will leave. So many people will leave from my group. So I'll be a bit more next year.
So, were you thinking about taking an experience?
Maybe next year I can take a little bit, but I like to be cautious a little bit from now. I mean, if I take too many students, the responsibility is become huge. So I think this year is the hardest year for me because these three master students, Ely and Qi Tuan and Zhao Ting. Yeah. Jigu Jiaxing had already told him he should think different direction. Anyway, we'll see.
You should also take care of your audience.
Yeah, from now I need to go to hospital and take surgery.
Hopefully.
8月刚放4月。
哦。
that.